on this computer. Okay, so I think my plan this time is to cut the lecture into portions so that we don't have to have uh, a large file for uploading into YouTube. Okay, so I think I still have they're giving me the licensed version, so now I can we can go straight for the lecture. But remind me that we will stop at around 12 o'clock to have a 5 minutes break, and then we continue at 12:05, okay, until 1 o'clock. So last meeting we discussed, we completed the Denavit-Hartenberg Convention, or DH Convention, as popularly used by most roboticists or robotics researchers around the world. So we finished the convention, the assignment, the frame assignment for any two consecutive joints. In this case, joint I and joint I and joint I plus 1, where in our case, joint I rotates about the Z I minus 1. This is the convention that we are using. Okay, so that means that joint I plus 1 rotates about ZI, which is that ZI, and also for joint I minus 1, it rotates about ZI minus 2. Okay, so we know that each joint, a joint rotates about, the joint I rotates about ZI minus 1. That's the convention. So every joint here, we're only considering rotational joints at this time, not translational joints. That means prismatic joints. Prismatic joints are the one that move like that slides, you know, that slides by normally by pneumatic or screw action or by hydraulics. Yeah. So those are the joints that other robots have. But for now, just for easy discussion, we are using rotational joints. So joints that rotates in this way. So yeah, so we have let me have this one. So you have this one, and then if this is the link and this is a joint like that. Now we're only considering like that. So there's one joint here, another joint here. So that is what we are. Oh, did I show? I didn't share my screen. Okay, sorry. So this joint I, and then it rotates about ZI minus 1, as I mentioned, and joint I plus 1 rotates about ZI, and joint I minus 1 rotates about ZI minus 2. So always the index of the joint rotates about the Z index minus 1. Okay, that's the for this case, this is the normal DH convention. There's a modified DH convention that is a joint I rotates about the ZI. But we won't discuss it in this class. In this class, we will just discuss the basic or the normal Denavit-Hartenberg representation by joint I rotating about ZI minus 1. Then we follow this convention about how Xi to be the common normal of both ZI and ZI minus 1. We mentioned that from last meeting. And Yi, we don't need to show Yi because it's just a coordinate that completes the right-hand rule. It's not very critical in terms of determining how the points or the origin of each frame is identified. So all we need to identify here in this DH convention is the critical Z axis as well as the X axis, or the ZI axis and the XI axis. Yi is not very, you can show it, or you can choose not to show it. And then from there, we identified 4 parameters. Okay, once you assign already the reference frames of frame I and frame I minus 1, then you will be able to determine the parameters theta I, alpha I, which are the angles associated with these transformation. There are 4 transformations that we will show that is being done in this to describe 2 adjacent or 2 consecutive joints using DH convention. So there are 4 transformations that are 2 rotations based on theta I and alpha I rotations, and translations based on DI and AI, which are of course distances. And so we say that there are given those four parameters for DH convention, we can transform using four basic transformations from the frame I minus 1 into frame I. So in this case, frame I minus 1, this is frame I minus 1. We choose to have its origin here, and then frame I with origin here. Okay, so the relationship between frame I minus 1 and frame I can be defined by these four parameters. And how are these four parameters being used? It is being used based on the four basic transformations. That is, transformation of translation along the z-axis, and so translation only. We mentioned already. I hope I can get. The not so good thing about Zoom is that it doesn't have, or it does have a spotlight. Okay, let me check. Oh, it can. Okay, maybe it's me that's not familiar. So here, so this translation only. So we already consider the position part. Yeah, this the vector of position only. So because it's translation along the z-axis, so z-axis is one, x, y, and z. So the di is here. Okay, there's no rotation, and so rotation is identity. So any question about this transformation matrix? No? Okay. Then the next transformation is about a z-axis of rotation, theta about the z-axis. And so rotation, this is the rotation part, and this is the position part. Because there's nothing on the position, there's no transformation in terms of position, so all these will be 0. And now we are just doing rotation. So rotation here, so about z-axis, so again, this is 1. Okay, for the z-axis, z doesn't change because it rotates about z. Only the axis that will change are the x and the y. So cosine theta here, we know that already, minus sine theta here, this side, the off-diagonal terms. Okay, so that's the transformation about z, about theta, about transformation about z by the angle theta. Okay, so next is the translation of position only along x-axis. Again, x, y, and z. So x-axis is AI here. So AI, no rotation, so this is identity. Okay, so I have to tell you that if it's no rotation, it doesn't mean that the rotation matrix is all 0. It will be identity. It means that no rotation about x, no rotation about y, and no rotation about z. All the axes are coincident. Okay, so that means no rotation. So it's just a translation along the along the x-axis. Okay, so that's that one. The next is the rotation about the x-axis by angle alpha. So again, position is 0, and then rotation by the x-axis. Here, rotation about x-axis, so x is 1, 0, 0, and 0, 0 here. So axis x is coincident, nothing, no transformation, no rotation. So again, cosine here, cosine of the diagonal term by alpha, and sine minus sine in the off diagonal terms. So we know this to be the basic transformation. 4 of them we multiply, and then voila, we get this transformation matrix. Okay, you don't need to memorize this. I will give this formula for you during the test, but in case you forget and then somehow you don't know, for you to still compute what you need to do, just remember about the z transformation about z by d, distance d, rotation about z by rotation like this, and transformation x, and rotation about x like that. So how does it mean physically in terms of here, in terms of what we are doing when we're doing all those 4 transformations? So let's check that. So for example, okay, maybe I want to use an arrow. So for example, in this case here, so we say translation along the z-axis by here, translation along the z-axis by a distance d. So the distance d is this. This is the origin. First of all, let's draw this. This is the origin, okay, of the the origin of frame I minus 1, and then we're going towards the origin of frame I. Okay. In that transformation, what it does is that this frame here will coincide once we do all the 4 transformation. This the direction of the frame I minus 1 becomes now the direction and the position of frame I. Okay, becomes coincident with frame I. So from this position and orientation of frame I minus 1, we do all those 4 transformation so that now frame I minus 1 becomes coincident with frame I. So how is it being done? So now let's do one by one. So transformation of DI along the ZI axis, or the ZI minus 1 axis. No rotation. So what happened here is that we move. Okay, we move this to that by a distance D. Okay, maybe not the. I cannot. Okay, maybe let's make a different color. This one. Okay, we move by a distance D from this origin. Okay, from here we translate the whole frame to this point. Okay, so now there is a new origin of frame new origin of frame I minus 1 and 2. Okay, now I want this one. So the origin becomes here. Okay, and again, this is still ZI minus 1. Okay, ZI minus 1, the same direction, I minus 1. Okay, here is XI minus 1, this direction. Do you understand? I'm just trying to show what is the effect of that transformation. Okay, so we transform this reference frame. The first transformation is we translate along the ZI axis. So we translate, that means that we move this origin of this frame into the origin of that frame. So now if we move this entire thing without rotating, no rotation, we move it. So now your ZI minus 1 is here. Okay, your XI minus 1 is there. Same direction. Of course, your YI minus 1 is in that direction. I'm not showing that so that it won't become, our things here won't become dirty. Okay, so we move the origin to that point by a distance D. That is the distance DI. Okay, that's the first transformation. So after the first transformation, the frame I minus 1 becomes here. Okay, now what is the next transformation? Next transformation is rotation about Z by angle theta. Okay, now this is your Z. Okay, this is still your Z now. Okay, you rotate about Z by an angle theta, or theta I. This is theta I. So from here, so positive direction, or you rotate from here to there. This is that one, from here to there. Now this is your theta I. Okay. Okay, so when it happens, what happened now? After that transformation, your ZI minus 1 remains in that direction because you only rotated about this, no translation. So what will happen is that this XI minus 1 becomes here. That is the second transformation. Okay, your ZI minus 1 is still here. Okay. So now there are two transformations. We move this point, move it to there. This is the first. Now the second one is rotate this axis into there. Okay, so now your ZI minus 1 is here, or XI minus 1 is there. Okay, Then the third transformation is that you move along the x by a value of AI. Now, move along the x. Where is the x? This is the x-axis. Move along it by a distance AI. There, that's AI. So now the third transformation. This is AI, that's the distance. We move this. We move this origin into there. So we move that origin into there. So now your ZI, okay, parallel, that is parallel and this is parallel. That is your ZI minus 1. And then your XI is in that direction. There you go. Okay. So after the third transformation, you change the origin. You translate that origin from here into that. So now this is the new origin. With the orientation of the axis is still the same because the third transformation is only a transformation of position. There's no orientation change. Okay. Then as you can see, the last transformation is rotation about x by angle alpha. So this is your x. Rotate x by an angle alpha. So here, you rotate it about here. X remains the same. And you rotate it there. So now this one becomes your ZI minus 1. Okay. So after the fourth transformation, your ZI minus 1 is coincident with ZI. And your XI minus 1 is coincident with XI. There you go. Okay. So the principle really of the four basic transformations in the DH using the DH parameters is that you perform those four basic transformations in such a way that your reference frame from ZI minus 1 from the I minus 1 reference frame position and orientation, you move towards the frame of I, the I frame, using all those four parameters for the four basic rotations. That's all. In this case, we can say that, just to visualize it, we can say that you transform your frame I minus 1 four transformations in such a way that your frame I minus 1 becomes coincident with frame I. Okay. Any questions with that? Okay, we did it last time. We stopped in the four. We stopped in the four transformation matrices, but we didn't discuss physically up to this kind of transformation to visualize what's going on. Okay. Any questions? No questions? Okay, if there are no questions, let's move. It's a problem here because you have to stop annotating so that you can. Okay, there. So those are the four transformation matrices. I mean the four basic transformation, and we know You already know this. We already discussed the inverse of the transformation matrix. The inverse of the transformation matrix is not the same as the rotation matrix. The inverse of the rotation matrix is what? Is its transpose. Yes, right? But the inverse of the transformation matrix is different. Okay, so for example, this one, okay, if we assign this to be, okay, we call it rotation of from I-1 to I, then this can be a position from I-1 to I. So when we take the reverse, to take the inverse, instead of from I-1 to I, we take the inverse. That means we take it from I to I-1 in this case. So how do we do it? So we discussed this one already from previous meeting. We say that this part, in case you don't have this formulation, you can derive it yourself. So that is already the I-1, still the I-1 to I transpose. Okay, check if that's really the transpose. Cosine, sine, there. Then cosine minus this one is here. And then here, the second row is the second column, cosine minus sine. And then third row is the third column. Okay, that's the transpose. Okay. So next here, what is this part here? Okay, we say that we change that. Okay, we already shown this before, that we change the direction of the position vector. Okay, if this is frame I-1 and this is frame I, okay, and this is your position frame, to say this is position of from I-1 to I. Okay, that's your position vector. Okay, now how do we express the negative of that? Okay, I mean, how do we express the other vector? Sorry, not negative, I am getting ahead of me. How do you express another vector, the same vector, that instead of from that direction, from this origin into that, you change the reference frame. Okay, so there are two things we need to do. First is that we take the negative because the direction changed. Okay, so to get this part, the pi to I-1, okay, to get this green vector, we need to take the negative of the pink vector, I-1 to I, but at the same time change the reference frame. Okay, based on which reference frame now, it will be now based on frame I. And so because we need to change the reference frame, that is frame I-1 into I. Okay, wait, let me undo so that it will come clearer. Okay, maybe let me, just to be very clear. Okay, I'll make it pink because it was pink there. So I-1 pi. Okay, take the negative of that. Okay, that's the first step. And now, because we need to change the reference frame, now you'll have to express it from I-1 into frame I. So now you need to have the rotation, change the rotation into frame I. Okay, so that's what's happening here. You take, first of all, there's negative, so now the negative, everything becomes negative, that's negative part, and now the pi, and then they change this pi multiplied by the transpose by this one, the transpose of that. This is that one. multiplied by that, it will come out with this one. Okay. So anyway, any questions with that one? So in especially if you advance further, you can see, you can have this transformation. You can do many manipulations of vectors into different reference frames. This is one of the basic information that you need to know. Changing the reference frame of a position vector. Okay. So let's continue. Now I think we are ready to assign or to investigate the DH parameters and the transformation matrix from the base frame to the end effector frame, in this case for the planar robot that we have considered for a very long time. Okay, so we say that in the planar robot, we have used this analytical method to come out with the position of the end effector frame with respect to the base frame. Okay, we did it before by expressing, in this case, X and Y in terms of the forward kinematics equation. Remember, like we have L1 cosine 1 plus L2 like this. L2 cosine of theta 1 plus theta 2 plus L3 like this, yeah? L3. L3 like that, cosine of 1, 2, and 3. Okay? And then you have in the Y direction, you have 1 sine like this plus L2 sine of 1, 2 plus L3 sine of 1, 2, 3. Okay, your 1, 2, of course, is theta 1 plus theta 2. 1, 2, 3 is theta 1 plus theta 2 plus theta 3. Okay, and then we can compute now what is your X and Y. But this case now we are going to use the DH convention, if whether we can still get this information. Okay, so now let's see. So you have your what did the DH convention say? First, into assignment, let's go back. Before we can get the DH parameters, we get the frame assignment first. So joint I rotates about Zi minus 1. Okay, so let's do that. So all of these rotations, all of these joints, you'll have Z. Yeah, so that one, another Z, another Z, and another Z that is just parallel. Okay, and the origins, for convenience, we assign them at the joint itself. Okay, I mentioned this one before in the last meeting, that the base frame can be arbitrarily assigned where your X, Y, your X, the direction of your X and the Y is, but your Z should be, your Z0 should be the axis of rotation for joint 1. Okay, so in this case, this is Z0. So we choose to have X0 in that direction. This is X0 and Y0 in that direction. So let's just concentrate on the X0, Z0, and X0. Now, this is your Z1, of course, and this is your Z2, and this is your Z3. Now, the question, sir, why do you have Z3 here when you don't have a joint? It's not rotating about anything. Nothing is rotating about that axis. Anyone? Nelson? Casey, are you there? Are you sleeping?
No, sir, I'm here.
Okay. Okay. Why? Why do you think we have the Z3 there? Nothing is rotating about that axis. What do you think? No?
Sir.
No?
Sir.
Yes. Are you in the same place, Chicago and KHC? Are you in the same room? I think you're in the same room. Okay, yes. You want to say something, Chicago? One? Inque? You want to say something, Mr. Inque? No? Okay.
So
Yes. Who's that?
I think that we need Z3s because we are going to use it, I think, as the if reference point of Z2, I think. I'm not sure, but I think that.
Okay. Why do we need it there? Why is it there at the hand?
So that is where we're going to match the axis of Z2.
Okay.
So
Yeah.
I think the reason why it's there is because even though we're not rotating it about, even though it's not a joint and we're not rotating it about its axis, we're rotating it about the second free, Z2.
Sorry, Mr. Twala.
It's gonna move in reference to Z2. That's why you have Z3 there.
Okay. Yes, but why we should put it at the hand? I mean, why is it there? There's nothing that is rotating about it. Is that okay?
Isn't it for the position, sir?
Yes, we choose its point, its origin to be here at the hand. And so we assign our point of frame 3 at the hand. So we say frame 3 is here. And then now Z3 is here. But nothing is rotating about Z3. Is that okay?
Z3 there.
We say Z0, joint 1 rotates about Z0, joint 2 rotates about Z1, joint 3 rotates about Z2. But Z3 is here. Nothing is rotating about Z3. Is that okay to put it there?
Yes, sir.
Why?
Because when you're rotating, when you're coinciding, you're supposed to coincide Z3 into Z2 with theta. So it needs to be there for you to determine how how much theta you're gonna rotate to coincide it with Z2.
Okay. Okay. Anyone else? Any guess? It's okay. I mean, it's just, you know, there's no wrong answer. It's just like there's a good answer a better answer. That's all. Because in this generation, people so bad when you tell them that it's wrong, you know. In the generation of my grandparents, they will be beaten by the Spaniards if they cannot answer properly. There's a long stick, beaten, physically beaten. But nowadays, people cry, will complain. But they learn fast with the beating. Anyway. Okay, come on. What's the answer? Okay, I mean, there's no right or wrong answer. Again, okay, anyway, so it's going to be 12 o'clock. Let me just finish this and then we'll take a 5 minutes break, okay? So now, the point here is that, of course, we need a reference frame to be put at the hand of the robot. We need that. We need a frame attached to the hand of the robot, okay? Because we really want to know how does the hand move with respect to the base, right? We know we want that, yeah? So in that case, there must be a reference frame here at the head. We want to put it there. Okay, yes. Okay, we want to. And then what kind of transformation is this? Again, the transformation from the frame 2 to frame 3 will follow the DH convention. Yeah. So now, for convenience, most of the time, okay, we use this reference frame, the last reference frame or the reference frame of the N effector to be coincident with the last, the I minus 1, I mean the N minus 1 reference frame. That means the reference frame just before it. Okay, so in this case, Z3 is here and Z2 is there, just for convenience. But nothing is stopping us because here there's no constraint to say that it's rotating somewhere. We can also assign our Z3 to be in that direction. That's fine. Okay, because there's no constraint there. Okay, as long as we follow, if we assign Z3 there, and is there any violation in terms of the DH convention? If there's no violation, then it's okay, because the DH convention, the DH parameters only is effective or only is true when you follow the DH convention of frame assignment. If you don't follow them, then it's highly likely that when you do the transformation from the frame 2 to frame 3 will not be correct. Okay. Okay. For example, if you when is not being followed? Okay, not being followed when any of these, like for example, this one, x-axis is xi common normal to both, like this. Yeah, joint I rotates about this. This one is N effector, so there's no joint that's rotating. Is xi common normal intersecting the zi and zi minus 1? Okay, this one, is it true? Okay, let's check. Is x2, if we choose z3 to be here, is x3, yeah, is x3 common normal and intersecting? It's normal and intersecting to both z3 and z2. Okay, so this is z3 and this is z2. Okay, let's check. Let's check that. I'm just for curiosity if it's really okay to. Okay, we choose to be here, and this is your z3. Okay, and then now, okay, if that is your z3, where is your x2? I mean x3. Okay, it could be this in the plane, or it could be like this one. Okay, it could be this that's parallel to z2. Okay, so in that case, is it intersecting? Is x3, is it common normal to both, normal and intersecting to both z2, I mean z3 and z2, normal and intersecting? Okay, let's check the normality first. Okay, is x3 normal to z3? Yes. Okay. Is X3 normal to Z2? No. They are parallel. Parallel is not normal. Okay. And is it, that's the first violation. The second violation is that did it intersect? It's normal, common normal, and intersecting, both Z3 and Z2. Well, it intersects Z3, yes, because they are in the same origin. But did it intersect Z2? No. Okay, so you cannot use this. So the best way, what people do is really to just, you know, become coincident. The easiest way is without even thinking a lot, become coincident with this one. Z3 is coincident with Z2. I mean the coincident in terms of direction. If that is the case, for example, this is your X3. Now, did it follow? Okay, did it follow that convention? Well, okay, is it normal? Normal to both? Yes. Is this normal? Okay, maybe let's just transfer here so that we can easily see it. Okay, is this normal? Yes, because okay, this is out of the paper and that's on the paper. This is normal. X3 is normal to Z3. Is it also normal to Z2? Yes, because again, this is on the paper, on the plane of the paper, and this is going out of the paper. Is it intersecting Z3? Yes, they're common. They have common origin. Is it also intersecting Z2? Yes, because this axis here along this line is intersecting. So both requirements are satisfied. Okay, so if you're not very sure, just check with the convention. That's it. Okay, you must follow the convention for the parameters to be correct, and then for your transformation to be correct. That's it. Just follow the convention because that's what it is. Okay, if you make it well, of course you can make your own convention. You know, if you want to change, maybe you see that this convention is not very general. You can make your own convention and just follow the convention. Make sure that everything, you know, is according to how you planned it, and check and verify that it's correct. Okay, there are other conventions probably that people have done, especially in terms of modified DH convention that I mentioned about. That in terms of joint I rotating about Zi minus 1 is joint I rotating about Zi. Okay, anyway, let's have I think this time is a good time to break. And then once after 5 minutes, we come back, we will continue with extracting. Now we know already the Z axis, you know, direction from Z0 to Z3 up to the end effector. Okay, now we need to check where are the X axis direction for each reference frame. Then after that, we check the DH parameters, the 4 DH parameters. Okay, see you in 5 minutes at 12 o'clock. Okay, I have to stop this for. Okay, see you at 12 o'clock for the same link. Okay, bye.